Okay, so before I begin the talk, I want a recap or introduction to singular perturbation theory, which we're going to need throughout this talk. So let's look first at this very simple differential equation with these two boundary conditions. And here the special thing is that epsilon is an extremely small parameter, like think 10 to the power of minus 20. Okay, it's extremely small. So like normally when we see a very, very small parameter multiplying a term, we would tend to throw away that term, right? The first instinct is to say, let's look at just this part. But then obviously it's not going to work because the small parameters multiplying the largest derivative, and if I throw it away, I'm going to not be able to satisfy both boundary conditions. So in this case, this equation is simple enough to solve, but in cases where the equation isn't, there are many nice techniques by which you can simplify singular perturbation problems and get analytical solutions, which we will. So in this case, if I threw away that term, I obviously can satisfy one boundary condition, but I do really miserably near the other boundary. And this thing is famously called a boundary layer, where there are sharp changes in a layer of order epsilon to the power something, depending on the problem, you can get very different behavior. And this we are going to see in the thing that follows. So now I can start my talk. So I thank the organizers for this opportunity. This work was done by Rahul Chajwa and Rajarshi along with Sriram and me. Rahul is, they both are ICTS PhD students, and Rahul is now postdocing in Stanford, and Rajarshi is still here. So what are caustics? Just think of caustics as singular features in something. It could be light intensity, gravitational things, planets collected together, or what we are going to talk about, suspension. So like just think of extreme levels of clustering where the number density is diverging in some regions. That is caustics. So clustering is well known in inertial particles. So like particles which have inertia tend to leave vertical regions in a turbulent flow, and they tend to collect in strain dominated regions. This is well known. Clustering is also known in active particles which do not have inertia, and today we are going to talk about this thing. So like what happens in the neighborhood of a vortex. So suppose you have a vortex here, and so there's flow going around it. Suppose you have a passive particle. The passive particle is just going to passively execute circles. Inertial particles want to follow the flow, but they have a reluctance, so they follow it with a little gap in time. So by the time this particle has gone straight, it's forgotten to follow the streamline, so it's going to execute a spiral. And those can be shown to be Fermat spirals under certain conditions around a vortex. So we're going to ask what happens to active particles. That's the question. And for this thing, like, let's remind ourselves, we're looking at particles in dilute suspension in a very large scale flow. And we're going to do what is called one-way coupling. So imagine that the ocean is going to tell the bacteria where to go, but bacteria cannot push around the ocean. So this is one-way coupling where the flow tells the particle what to do. And so the flow is independent of the particle. It's a very large scale flow, so it's at very high Reynolds number. So that's the Navier-Stokes equation. The flow is incompressible. So to make our life easy, what we're going to do is look at one vortex in a flow. So here's a cross section of a 2D turbulent flow, and these are vortex patches. You will see that a lot of the vortex patches, some examples are shown here, have Gaussian vorticity profiles. So a Gaussian vortex or a Lambosine vortex, you can think of as a kind of Drosophila or a building block of turbulence. So if we understand what's going on near one vortex, analytically, hopefully, we will understand something about what's going to happen in turbulence. So that's the basic aim of looking at one vortex. A Lambosine vortex has this velocity profile, which is a function of r, where delta is its thickness. And as delta goes to 0, the Lambosine vortex goes to a delta function, basically a point vortex, and we know everything about the flow around it. Okay, so now we're going to look at a single vortex, and we're going to ask about caustics formation in the neighborhood of this single vortex. And the thing is, caustics are going to form whether the particle is inertial or active. And there's going to be some differences. So what are caustics? We'll talk right now. But the basic idea is that here is a teeny tiny vortex. Its scale is much, much, much smaller than the scale of the flow. And there is an epsilon neighborhood around it. And this is going to make a singular perturbation problem. So the point is, remember the problem we looked at earlier? So if you're living near this boundary where the vortex is, you are going to be showing very different dynamics from if you're far away. So far away, you can kind of ignore higher order terms in the equation, and near the vortex, you have to keep all the terms. So this is the basic summary of what we are going to see. So what are caustics? So we are going to put two rings of particles around this vortex, and we're going to ask, does the red ring of particles overtake the black ring of particles? And if the red ring is going past the black ring, then we're going to call that caustics, because at that place, these two things are coming very, very close together and they're occupying zero volume. So this is going to be the definition of caustics. So remember that if we're running field equations for the particle, like suppose I say that V is the velocity field of particles, then like in the caustics region, we cannot define a V because particles are dashing against each other. So field equations are going to work in non-caustics regions, but they're not going to work in caustics regions. So let's define caustics properly before we go along. Here is U, the flow velocity, and here is V, the particle velocity. And the del dot U is 0 because the flow is incompressible, but note, the particle field is not incompressible. Particles can cluster, 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 and del dot V can be big and negative. So what we're going to define as caustics is when del dot V tends to minus infinity. So like, it's a funny statement, but when the divergence diverges in a negative sense. So that is caustics for you. Okay, and it's not describable by a field in that thing. So a caustics event is thought much more, you can think of it much more simply as two particles are just coming and dashing against each other, and they're occupying they're zero volume particles, zero radius particles, and at the same place we have two V's. So obviously a field cannot have two V's in the same place. So this is the definition of caustics. And before we go to active particles, let's talk about inertial particles, and then we will see the analogy with active particles. So here are inertial particles, and because they're inertial, they are in unsteady Stokes flow, and that's important. Like otherwise, in activity, very often we consider them as being in steady Stokes flow, which is what we'll do. That's the basic difference between inertial and active particles, okay? So a small, heavy, spherical particle which is inertial follows what we in our group call the baby Maxi-Reilly equation. We will talk about the full Maxi-Reilly equation briefly later. So this equation is simply written down as this, and the Stokes number is like basically small for most particles, and so this is forming our famous singular perturbation problem. So there's a small parameter multiplying the highest derivative. Remember that this is the second derivative of the spatial location of the particle. So, and U is the flow velocity, V is the particle velocity. The particle has a radius A, and its Reynolds number is much, much less than 1, but it's still in unsteady flow. Because the Stokes number, this effect doesn't go away because of the singular nature. So now this Stokes number is briefly the time response time of the particle divided by a typical time scale in the flow. So this is basically the simple equation, but it's highly non-linear because U can be anything you like. You can be a turbulent flow, and the location where you take V, this X location is, the U is taken at that location. So the whole story can become quite complicated even though the equations look pretty baby. So like now we did this for a single vortex. So we now put inertial particles with those simple equations in a single vortex, in the neighborhood of a single vortex. And we just ask, when does the inner ring overtake the outer ring? That's a simple definition of caustics. And we write down the time for caustics formation on the y-axis here, and the initial radial distance from the vortex. So like from the center, we check the initial R0 you can think of. And we've started 2 rings at very, very small delta R0. So wherever delta R0 changes sign, we say caustics have occurred. The time taken for caustics to form suddenly diverges. So what this means is, if I start these 2 rings a little outside this radius, I've scaled it by the epsilon, that's why it's a small number, but in order 1 in epsilon, there's going to be a place where the time for caustics diverges. So outside this radius, if I start 2 rings of particles, the inner one will never overtake the outer one. Whereas inside this special radius, the inner one will overtake the outer one, and it's order 1 in the particular non-dimensionalization that we have. So that is the basic summary. There are special regions in the flow, in a big turbulent flow, where there are sharp, tiny vortices where caustics can happen, and nowhere else can caustics happen. This is basically the summary which you're getting from a single vortex. Something slightly different will happen in full turbulence, as you will see. So just to remind you, this singular perturbation problem, the character inside this boundary layer is very, very different from the character outside the boundary layer. Outside the boundary layer, you can safely throw away this term. Okay, so like now, active particles don't have inertia. So they're in steady Stokes, namely, this term doesn't appear anyway. So where does anything interesting come from? That's the question we want to ask. Is there a time thing? Okay. That includes questions or? No. Okay. Okay, so we're writing this equation for active particles, where the Reynolds number of the particle is small, the Stokes number is also 0. So now it's like in a steady Stokes, and in typical steady Stokes, you'll have velocity given by mobility times a force. And in our case, we have this Hookean dimer as our active particle, which is basically an active AOUP. Let me be safe and say it that way. It's a generalization of a standard AOUP, which is a Hookean dimer with a stretching W. So you have these 2 blobs which are stretched by a distance W, and this dimer, a bunch of these dimers are sitting near our single vortex. So that's the flow we're considering. That's the situation we're considering. And so the velocity of this dimer also has a contribution coming from its size. So the more it stretches, the more it moves along its nose. So that's this term. And this is like the flow velocity, which is telling the particle where to go. It's the ocean which is telling the bacterium where to go. Now, the W itself, the stretching of this dimer, has its own equation, which is from AOUP. But basically, it has a relaxation time, and it has a response to the flow. S and O are the symmetric and antisymmetric parts of the velocity, the flow. Okay, so then if there is an antisymmetric part, the W rotates. If there is a symmetric part, the W stretches by this factor alpha. That's what it is. And this term is just noise. It won't feature in most of our talk. And this term basically is, you know, like when you have a shear flow and the shear is changing, then the particle will tend to move in the direction. That will tend to move the particles, align the particle's nose in that direction and stretch out. So basically, if there's low shear here and high shear here, the particle will stretch, right? So that's what this term is. So this we'll call as the alignability parameter. So we will ask what all this brings to the story. And so like now this thing I can put back in that equation, and I can actually eliminate this size W from the equation, and I'm starting to get something which looks like an inertial particle. So this is like an equation for an inertial particle. So this, we saw a drag term here with the inertial particle, and now there is something which is behaving like a mass of a particle, which is basically coming from viscosity and this relaxation time for the length, for the stretching. So that is what this equation is looking like. And it's again very, very non-linear. Now, in this talk, we will not consider the external force to make our life easy. So we will be talking about this part. So in the ocean, so we are talking about this quantity beta, which basically determines the swimming speed. So we looked at a few living things in the ocean, and we tried to derive this non-dimensional parameter, which is beta is like a 1/time, and grad u is typical for oceans, the upper reaches of the ocean where these creatures live. And this is kind of the range, so that we know where to do our calculations. So this is kind of the range we see, and the Reynolds number for some of these is indeed very, very low. Now, initially it looks like, okay, the active particle is something like an inertial particle. It has this pseudo thing which looks like inertia, and that's the end of the story. So whatever we see in inertia, we can apply to the active particle, but no. It's a very incomplete analogy. There are these terms which are colored similar, which I won't read out, but they kind of stand for external force, drag, fluid acceleration, and so on. Whereas the noise doesn't appear in Maxi-Reilly unless the particles are very small, when they're usually not inertial. And then this added mass term is completely extra for inertial particles, and that brings new physics. So we should be careful about that. And there is this very important term called the Bassett history, by which an inertial particle remembers a lot about its past, whereas active particles do not. So this is an incomplete analogy we can talk to you about. Now let's put the active particle near the point vortex, the simple one where we know analytical things. The inertial equations which we had long ago look like this, and the active equations look like this. You can see that the black things are just come about again, but with the new time scale, but we've used the same non-dimensionalization here. And because of the non-dimensionalization, we've got rid of all the parameters. That's pretty clever, which it was a thought that Ravichandran thought about. So then these colored terms are the extra active terms, and we've set noise to 0 for simplicity. So then we're going to ask about caustics in this setup. So then the caustics we can think of in another way also. Like, I was talking about crossing of trajectories as being caustics. We can formally ask if the divergence is diverging. So we can write down the active equations for this quantity, the divergence, the trace of the divergence matrix. And this thing, we can solve this equation for this quantity Z, and we can ask where Z goes to minus infinity. So if Z is actually diverging, we are actually reaching caustics. So we can check this in two ways, and believe me, we get the exact same answers. So this is just a little more formal than just the simple crossing of trajectories. And we're asking, if you start at R0, do you cross someone who was at some other R, and that will be your R caustics. So this is like an initial distribution that we started with, and if you had only passive particles, they would stay that way for all time. Inertial particles vacate the vortex, void the vortex region very sharply, and have a sharp density thing which moves out slowly like this, a sharp density edge which moves out slowly. Active particles have like something pretty sharp, and then there is a diffuse layer, and sometimes they diffuse out slowly, sometimes they come back. It depends on whether it's AOUP, ABP, the details. But the moral is that the vortex gets voided, and there is a big density jump at the edge of this thing where the void is at the edge of the void. And so like with the singular perturbation theory, we could actually write down some analytical answers for the radius of caustics and the time at which the caustics will happen. And so singular perturbation analysis told us a lot of what to expect. So basically all the answers qualitatively we got from singular perturbations. But then just for completeness, we solve the whole complete equation. And you remember this diverging thing, except I've now drawn it on log scale. So this thing was for the inertial particle and this thing is for the active particle. So you can see that they're doing something very, very similar to each other. Like beyond a certain initial radius away from the vortex, if an active particle starts its life there, it's never ever going to participate in caustics. So if it wanted to participate in caustics and live in a place where lots of them cluster, its life is too bad for people who started far away from the vortex. So if you started near the vortex, you get lucky. And this is just a summary at different levels of that activity parameter alpha. So you have, again, like if you're starting near the vortex where R0 is small, you get caustics and otherwise no. So this is the summary for AOUP. You can get similar things with ABP, except it's more complicated and is not very amenable to singular perturbation theory. So here are 4 dimensionless groups in our problem. We talked about this beta guy before. We'll now see results with, this thing being written as A. And then this alignability thing, I told you how it stretches when the shear changes. That is the other parameter. We're going to mainly focus on these two. This one is kind of trivial, like if there was no tau, there would be no caustics or anything, as we saw earlier. The noise strength, we will just mention right in the very end. And just to make sure that everything we're saying is not very peculiar or very special to AOUP, we've also done simulations with ABP. So we put ABP and AOUP in 2D turbulent flow, and this is the equation for ABP, which I think everybody in this room will know. Okay, so here are the results. The Hookean dimer, AOUP, I called it Hookean dimer because there's no noise in it. And here is like no alignability with shear, and there are 3 levels of activity, as you can see. And these are caustics. Like, trust me, I've not shown you collision data, but these are caustics. So you have more caustics forming, and in all of these, you'll see it's not a homogeneous distribution. Here it's almost homogeneous, and here it's already, forming caustics, and here it's forming sharper caustics. So the moral is that at intermediate levels of activity, you get huge amount of caustics forming. So that's the finding. This is analogous to what happens to Stokes number in inertial particles. And now, like, we increase the alignability parameter, and you see like pretty sharp caustics. So alignability gives you more caustics. And then there is this thing of preferential sampling. So we saw for a single vortex how the neighborhood gets voided, right? Is that holding true in turbulence? That's the question we are asking in this thing. And so like this gray patch you see is the ambient flow. And this is called the Okubo-Weiss parameter. So where it is positive, it's vortex dominated, and where it's negative, it's strain dominated. So the ambient flow without particles, we just ask which place has what vorticity and what strain. And then we ask wherever the particles are sitting, what is the Okubo-Weiss in that place? And if particles are indeed voiding vortices, they should leave all the positive area and focus on the negative. Right? That is the measure in 2D turbulence that they are indeed voiding vortices. And certainly as you increase activity, it goes from here to there. Sorry about the color scheme, it's not brilliant, but it's leaving vortical. It's leaving regions of very high vorticity. That's the moral. And yeah, so these also, you can see how they concentrate in regions of high strain. Okay, so we look at the number density fluctuations. That's just another way to convince you. And the other thing that this again tells you is that as you increase alignability, the clustering increases. So this is just a measure of the clustering because we're talking number density fluctuations. But when they're very, very high, you're talking caustics. And as again, at intermediate levels of activity, you can see the most response. And we just plotted these 4 animals here in straight lines because we have no idea about their alignability parameter. But just to show you that their levels of activity are in the range that we are talking about. And ABP does the exact same thing, intermediate levels of activity. You see this, and you see slightly less response to alignability, but you still see that. And this is all deterministic. Just to end the story, I will show you a movie of, oops, a noisy case. And as I conclude, I want to make one important point which is highlighted in this thing. So like suppose we want to do simulations of a big ocean place with lots and lots and lots of particles. It's kind of crazy to try to imagine that you can simulate each particle. You cannot. So like it will be nice to have field equations for the particle at coarse grid and then solve it in that part of the flow, and then only in regions where you identify that there are caustics, which we already know, we can treat them as individual particles. And so we can resolve like things like collision in those. We checked that in the other regions, collisions and clustering is very, very poor. Whereas in the caustics regions, it's very, very high. So like we could actually split our simulations into two and get good answers. Thanks for your attention.
For the active particles, there was this alpha, right, which controlled how much it aligned to the shear flow.
Yeah.
But the Maxi-Reilly equations that you showed were for spherical particles.
Correct.
Presumably, there's a generalization for orientable or anisotropic inertial particles. And are there effects, at least with regard to shape and flow alignment, in inertial particles that are different or same to the active one?
Okay, so the short answer is we don't know yet. We are trying to do proper unsteady Stokes simulations for non-spherical particles, but that's a completely different story. Of course, even in steady Stokes, particles which are not spherical do bizarre things. So like with inertia, it's not at all an easy problem.
How should I think of it for an individual particle that it will eventually end up in a caustic and there's some frequency with which it enters and leaves this? Or will some particles just never participate in some small proportion and then caught in that?
Okay, so what we believe is that as the Reynolds becomes larger, 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 a vast majority of particles will never participate. Only those guys who are lucky enough to be near intermittent vortices, these tiny, very strong vortices, those guys will participate in caustics.
So what's the implication for this ecological question of finding mates for these unicellular organisms where they're at low density on average?
Yeah, so where is Vishu? If he can do an experiment, that will be great. We can see, like we can actually put vortices and see what happens to reproduction and things like that. But yeah, we believe there should be implications, or we hope there should be implications. What? I couldn't hear. Oh, you passed the experimental job to him. Okay. Let's hope somebody wants to do this. It's simple, guys. Like just take a magnet and set it rotating and put particles there. Yeah.
Rama, I was thinking about an implication would be for food for these large, big relative number creatures that live in the ocean. I mean, they obviously don't sense these vortices, but they would then be able to look at clumpy, small, shrimp or whatever that can be captured by these vortices. So I'm wondering whether that's what's happening in the ocean as well, because you see large, predators going after.
Yeah. Yeah, if you see like any pictures of these things in the ocean, you see that they are stringy or they are clumpy. So maybe these other guys, like they can just see it from far away and go there.
Out of its nose hole, and that traps a penguin or something, which like gets trapped into the vortex, and then the dolphin basically eats it. So I can share that video with you.
Okay. I have a suspicion it's not following Stokes' flow, but
this field, so this may be I'm new to this field, so this may be a stupid question. Inertial particles, typically you have to express it in phase space consisting of position and velocity. right? So if you express it in terms of position and velocity, do you still see divergence going to 0 in that phase space?
I would say yes. Because at least in active particles, what's happening at long time is that their activity goes away. Once they clump, their activity goes away and the velocity effectively goes to 0. And whereas other particles can do their own thing, like they're in other circles and they're going. So the radial velocity goes to 0, the tangential does not. So I think it will shrink in phase space as well.
But velocity
Position
going
velocity.
to 0 doesn't mean it is, well, yeah, I mean, all dissipative systems, ultimately the
No,
velocity...
velocity is going to a number.
Okay,
So
yeah.
it's shrinking in phase space.
Yeah,
There's a kind of attractive fixed point in phase space.
but that is true for all dissipative systems.
Yes.
Right? So the question is that for a dissipative system with external actuation by these fluctuating eddies, do you get the system going to a lower dimensional manifold in 6-dimensional phase space?
Okay, so I think yes, because once they reach these caustics regions, they take on some characteristic velocities. But that's a nice question about the 2D turbulence, which we can ask. Like I was answering from the single vortex point of view, but I think yes, but I have to check it.
Yeah, I mean, you can calculate the Lyapunov exponents, right?
Yes.
Yeah.
Yes.
And do they, is the sum of all exponents negative?
It should be. Okay. That's what I believe, but we have to check.
Okay.
If there are no more questions, let us thank all the speakers of this session.